Look at a pristine piece of decorative chrome next to one that is peeling, pitted, and dull. The difference between the two isn't about how well they were polished at the end of the manufacturing line. The peeling chrome failed because of microscopic structural flaws deep beneath the surface. Industrial chrome coating, or chroming, emerged in the early 20th century as a solution for aerospace and automotive manufacturing. Engineers needed a way to protect metallic parts from corrosion and mechanical wear while maintaining a bright, reflective finish. A hard, dense layer of chromium resists oxidation and chemical degradation. This made it highly effective in extreme environments, where parts require minimal friction and a consistent visual appearance to ensure they function correctly over a long service life. The quality of that finish, its uniform thickness and high gloss, is an emergent property. It is the direct result of controlling the crystalline grain size of the metal at the nanoscale. Producing a perfect chrome finish means balancing competing physical constraints. Engineers have to manipulate the chemical and physical state of the underlying substrate metal long before the first layer of chromium is ever applied. For any industrial coating to survive, it needs to grip the material beneath it. This is called mechanical interlocking. The substrate surface must be physically rough, providing jagged, microscopic anchor points for the coating to grab onto. However, a highly reflective, glossy finish requires the exact opposite. The macro surface must be completely smooth. If a surface has microscopic peaks and valleys, photons hitting the metal will scatter in random directions, creating a dull, matte appearance. This engineering conflict is the adhesion-gloss paradox, making the substrate rough enough to hold the coating securely, causing incoming light to scatter. But smoothing that jagged substrate to reflect light perfectly erases physical anchor points. The coating loses grip, delaminates, and peels off. Relying entirely on traditional mechanical methods to prepare the metal forces a compromise. You can have physical durability, or you can have a pristine, highly reflective surface, but you cannot achieve both. We can see this compromise by looking at standard mechanical surface treatments. The first is sandblasting, a technique used to clear away passive oxide layers. Abrasive masting violently and intentionally damages the bare metal substrate. This drastically increases the surface roughness parameters, measured as RA and RQ values. RA and RQ are metrics used to quantify the microscopic peaks and valleys on a material surface profile. This high roughness provides excellent nucleation sites, starting points for crystal growth, which creates high adhesion for hard, functional chromium coatings. But for decorative chrome, this macro roughness rumins the finish. Decorative layers are thin, meaning the jagged topography of the blasted metal translates completely through the top coat, scattering light and dulling the final appearance. The alternative mechanical method is polishing. Instead of gouging the metal, polishing aggressively smooths the surface down to a mirror-like baseline. Polishing drops the RA value effectively to 0, solving the light scattering problem, but doing so eliminates the mechanical anchoring sites. Purely mechanical approaches hit a dead end here. To get both grip and gloss, the preparation must move away from physical abrasion and down to the microchemical level. The first step is chemical activation. Manufacturers use a process called acid pickling. By dipping the polished metal into a targeted solution, they can alter the surface chemistry. A carefully timed acid dip dissolves unwanted passive oxide layers without altering the overall macrogeometry of the polished part. The acid mildly etches the substrate, creating a controlled topography known as micro-roughness. This provides just enough mechanical interlock for the chromium to grip, but is shallow enough that it doesn't disrupt the macro-smoothness required to reflect light uniformly. Precise chemical etching improves bonding, but it still relies on physical topography. To achieve an absolute mirror finish with maximum adhesion, engineers abandon physical topography entirely and manipulate the metal's surface energy. To get peak adhesion on a physically flawless, smooth surface, the substrate's chemical reactivity must be altered. This is achieved through atmospheric plasma treatment, an advanced surface activation method. Instead of acids or abrasives, a highly energetic wave of plasma sweeps across the metal, non-destructively stripping away residual organic nanocontaminants. More importantly, it activates highly reactive functional sites across the entire face of the substrate. This process increases two critical metrics: surface-free energy, and wettability. Surface-free energy is the excess energy at the surface compared to its bulk, dictating how strongly it will bond with another substance. Wettability is the ability of a liquid to maintain contact with a solid surface, driven by intermolecular interactions. This contact angle measurement compares a water droplet on an untreated surface to one on a plasma-treated surface. The spherical droplet indicates low energy. The flattened droplet proves a massive increase in wettability, allowing molecular bonding without physical jaggedness. Plasma treatment resolves the adhesion gloss paradox. It provides industrial-grade molecular adhesion on a physically flawless, mirror-smooth substrate. With a perfectly activated high-energy substrate prepared, the metal is ready for the final stage, electrochemical deposition. Historically, this process required massive infrastructure, using large baths of highly toxic hexavalent chromium to coat the components. Modern chroming shifted toward trivalent chromium baths, providing critical environmental compliance by replacing toxic hexavalent alternatives while maintaining the coating's structural integrity. During electrodeposition, the final aesthetic gloss is dictated by meticulously controlling parameters like current density and bath temperature. Plotting current density against grain size shows that tuning electrical parameters forces the metal to deposit in fine, densely packed microstructures. This dictates the exact crystalline phases that form, primarily the dense alpha chromium and delta chromium phases. As the current flows, countless geometric microcrystals rapidly nucleate and lock together. They form an impenetrable, perfectly flat, and uniform solid wall. These fine grain sizes and homogeneous phase distributions naturally result in an incredibly smooth, highly reflective surface. Techniques like pulse electroplating or magnetotron sputtering can refine these microstructures even further, reducing internal stress and minimizing microscopic defects within the coating. True aesthetic gloss is not something painted on or buffed out at the end. It is the physical manifestation of perfectly aligned nanoscale crystalline growth, driven precisely by electrochemistry. A flawless chrome finish is engineered from the substrate up, not the top coat down. Sandblasting raw metal yields high adhesion but destroys the possibility of gloss. Polishing the metal alone yields high gloss, but guarantees the coating will delaminate and peel. The successful sequence starts with mechanical polishing to create a flat baseline. Then, atmospheric plasma activation boosts the surface free energy, preparing the metal for molecular bonding. Finally, precisely calibrated trivalent electrodeposition controls the crystalline growth to build the dense, reflective coating. The result is a rigorous, repeatable process that produces highly durable, aesthetically perfect finishes on everything from aerospace components to the oven handles and sink fixtures of a vintage kitchen. In industrial design, a true mirror finish does not hide the underlying metal. It is the visible proof of absolute microstructural and electrochemical control.